So I guess like let's review a little bit what we left off last time. So did at the end we talk about dropout. Um, so basically dropout is a regularization technique that we simply during training just randomly like kind of, as the name suggests, I drop out some of the node there, like some of the new one there. Just pretend that they are not there. So like I have the new one here, like just randomly like erase that. So and then like we mentioned last time that like uh okay, testing, of course I will use the entire network, but like training, like each time we randomly drop some of these new ones here. So therefore if we think of like the amount of energy that pass through the network, or the amount of energy going out from the network during training, the energy will be smaller, right? So therefore we mentioned last time that like to make sure that the the energy is consistent, then during testing we should rate. I mean, we rate the the rate of the new ones. More precisely, if our draw weight is p, then we should scale all the weights during testing uh, by p as well. Right? So it's kind of like make it smaller. So so something like this. So basically, we'll have like doing forward pass. This is a training. Doing forward pass, like uh, we randomly drop out some of these nodes, right? So with this probability p here, and doing prediction, like we need to scale the weight by p here. So as we mentioned last time, at the end also, like it's often like we want to minimize number of operations as much as possible during prediction, because evaluation often, it's almost always that we want to, okay, we will operate many times, right? We want to, or maybe like in some real-time application, we even want to have this prediction can be done really quickly. So therefore, like maybe even though I think it's kind of silly, we can like drop these like things here. So instead of like doing this scaling at the prediction time, or doing evaluation testing, we can just like scale up uh, the coefficient by 1 over p during training. So okay, that's basically dropout. Um, and and also like I'd like to mention one thing about activation. As I mentioned, like I won't cover like activation one by one, but since we mentioned dropout, it may be kind of like a good time to kind of mention this GeLU activation function, GeLU. Uh, it's one of the reason, I guess it's like 2017 or something like that, and it's getting more attention now because it's kind of a default activation function used in Bird for NLP. Like I'm uh, I'm not sure GPT actually, but I use GeLU. I think GPT also. So basically the motivation of GeLU is I drop. It kind of like motivated the paper like with dropout. It's saying that okay, like dropout, we want to randomly like drop some of the new ones there. So in the sense, if I have some new ones and new ones, and then the next day new ones. So I have some inputs coming in, right? So I this input would be like, or like I can think of like this new one. Okay, maybe what should I do? This new one I can zoom in. Will be like have like a activation function here, some kind of activation function, and have like kind of like uh signals, say weighted weighted sum of signal like pass into the activation function, right? So what he uh the authors argue is that like, okay, I can have some random dropout as well, and he's thinking like I'm randomly drop out the parameter based on the input of the signal. So I'm thinking the input say random, right? So what he chose eventually is like simply uh he will say if I have x is larger than some value, then we'll drop that out. So precisely what he did is he have this activation function is defined as a GLU x defined as a x find x here, where this find x is basically the probability that x is bigger than x, something like, oh sorry, x less than x, where x is a Gaussian random variable with like zero mean is equal variance of one. So then like so that find x therefore will have a shape something like, let's see, it's less than x, right? So if I have a very big x here, then the probability will be one, right? And then when x is small, it will go to probability is equal to zero. So it's like something like uh like a sigmoid function, something like this, right? Like that. So in practice, it also like approximate this as a sigmoid. So we approximate this as say x times sigmoid 1.702, something like x, something like that. And so then the GeLU, if you okay multiply this find x with x here, you get this activation function. It's more or less like this, have this shape here. So I guess the name GeLU is just coming from the fact it's like kind of like have a similar shape as VeLU. It's like a kind of, what should I say, a smooth version of this VeLU activation function. And it turns out it's just the performance is good. It showed that like it give like better performance in several cases. So therefore, like now more and more people try to use this. Maybe in your project you can try to use that as well. And anyway, like it is implemented in Torch, and I'm sure it's implemented like in TensorFlow as well. So okay, this is a side note about GeLU. And let's see. So next thing I like to talk about is optimization. So maybe I can directly go to the slides. Maybe I don't know. Usually it's better to scratch, I guess, to draw like because I slide. I think sometimes it's a little bit hard to follow. Oops, what happened here? I probably need to read. Okay. Huh. I don't know why it's untitled. Okay, anyway. Okay, let me just start a new terminal. So data augmentation, I yeah, I will skip that for the moment. Maybe I will come back to that. But anyway, like I guess I just a remark here, like data augmentation is you should always do that. And think of like if you have the simplest case is like for example here, like if I'm doing like classification, I have some for some images, I trying to classify cat versus not a cat. Then you have a set of training data or training images. I can always augment more training images by simply like modify this image a little bit, right? Because to human, this is a cat. If I rotate by like 10 degrees, it still look like a cat, right? And then like if I change the intensity a little bit, make it brighter, or maybe I do some enhancement on the image, or even I add some noise there, it still be a cat. So then like you can do lots of this kind of like operation to make it like um, um, kind of augment your data, training data to make more training data. And this kind of tricks has been used throughout and now become more and more sophisticated. For example, like people talk about self-supervised learning. It's really a data augmentation technique. Um, we may get into that. I see like how the time how our time I mean how much time I have like so but like if I don't have enough time to go through that, so you just need to know that okay, data augmentation is something a very simple idea. Everyone um can understand it. It's just common sense. So and okay, this some other regularization tag. I will just skip that. Okay, I would like to go to talk about like optimization. So eventually we say like most optimization technique used to train neural networks are just one uh, first order and second order. First order will be just like steepest descent, but different variation of steepest descent. And second order will be like variation of Newton's method. So for the first order method, so of course, like the simplest case would be just steepest descent, as I said, right? So we have the step size. Here is like often known as the learning rate here. Learning rate. And we need to compute the gradient somehow, right? This uh usually by okay, just make sure you guys are here. How do what by what means we compute the gradient? Uh how to you can just give me the name. How do I what's the technique used to compute the gradient here? Yeah, yes, the gradient is the derivative. Yeah, it's a partial derivative. But how do we compute that like in the network? Remember, we have like layers of network. Uh, it's very hard to compute the derivative. You know this is like basically I have the weight here, right? That's W. I want to know like how this the final loss is going to change according to this W, right? Yes, that's the backpropagation. I'm looking for that word. Yeah, that you need to use back. Typically, I just doing backpropagation to find the gradient. Now we find the gradient, then just do kind of like gradient descent right here. Uh, but sometimes there's a problem like for gradient descent. Like here is an example. Like if I do gradient descent uh naively, what's going on is I think of this point here. Uh, okay, again, a simple question to check your understanding. I guess this is the level set, like this is a function of, so I guess I need to mute one of you guys here. So I have this is basically a function. You can imagine maybe this is the minimum here. We want to reach here, right? So maybe like this is a 10, this is a 20, 30, 40, and 50, and so on, 60, right? So what's the direction of gradient? So A or B? Maybe I give several options, or C even. Or what's the gradient in this case? What's the direction of the gradient? Okay, so in this case again, the majority is actually incorrect. uh, so no, that like if you forget anything about the math, the one most important thing you should realize is that what is the physical meaning of gradient. The physical meaning is like if you in like somewhere inside the hill, the 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 physical meaning of gradient is the direction. Okay, the direction of the gradient. The physical meaning uh is the direction going uphill, the steepest uh direction going uphill. That's the gradient. So for example, like if I have like this point here, um the steepest direction will be somewhere like this, right? So I probably I don't know how to draw this. This is I'm not a great painter here or like artist here. So if I have a maybe I have a point here, like this point, like if I project to the XY plane, maybe something like this is the X and Y axis. So more or less say if you're going uphill, maybe this direction. So maybe like going this way. It's going uphill, right? So in this case, so therefore, like where is going uphill? I have this is 50, right? And this level is 60, right? So going uphill should be this direction, right? Going this C direction, right? So that's the direction going uphill. That's the gradient should be pointing at this direction. Now, and if I use like steepest descent, what happened is like, for example, like I start from here again. I start from at this point. I want to descend along the direction, basically the opposite direction of the gradient, right? So I go this direction. Therefore, maybe I have the learning rate is something like that. Maybe I say a little bit big the learning rate. So I jump to this point here. So in the next step, I also like, okay, find the gradient. So it's like the gradient is this way, but I will point to the opposite direction, right? So I will go this way. So this way, so maybe like my learning rate again is too a bit big. So I would hop to here. And then next time I hop to here and so on and so forth. Actually, you see it's pretty bad. I will have something like this, oscillating like this. So of course, like, if your learning rate is smaller, that will help you. But at the same time, it's this bad because we don't what sorry we don't apply any kind of like what's that inertia or smoothing or what's that better word for that? I'm thinking on the gradient itself. Momentum, yeah, that's the word like you say is momentum, like. But actually, I like inertia better. I think there's a uh, control word for that also. In control, what do we damping? Oh, right. That's if we damping. Oh, like yeah. If like we we try to kind of like smooth this. Okay, this this gradient itself. Then what happened? Like you see the gradient is like always going this direction and this direction, right? If you decompose this gradient, you have to do two components, right? One along this direction, one along this direction. So you look at the gradient here. Um, I have like maybe like so much component in this direction and a little bit component in this direction. And if I look at the gradient at this point here, or the negative gradient at this point, I have like so much in this direction and a little bit of this direction, right? So if I kind of like do a moving average or I smooth it, try to smooth it, or like apply momentum or whatever you call it, then you will cancel this vertical oscillation and reinforce this horizontal like direction here. So it will smooth out a bit. So if I do a trying to smooth it a little bit, I will have something like more or less like maybe still oscillate, but I oscillate a little bit less like this instead of like going that. So and will be like going that faster in a faster way. So and that's like this damping or like momentum or inertia. So I can yeah, this is just repeating what I said. So I can do it using a moving average, right? The simplest thing is I just doing a moving average. So instead of doing Okay, this slide I guess is redundant. I guess I can skip that. So instead of like you trying to uh, just update with this thing directly, right? So I will update the moving average of this guy here. So the moving average will be computed as the previous past, previous accumulated values, like this total accumulated one is delta x, let's say. Then each time I will not have delta x exactly equal to this guy, but will be a weighted sum of the previous delta x and the the update right here. Right? So if I have mu, okay. Oh, okay. I already showed that. Okay, I want to ask you when is that no momentum? So if I set mu equal to 0, then we'll go back to the case that's no momentum, right? So this will be 1. Sorry, like this will be 0, and then this will be 1. So we will just get back to the previous case that so delta x is equal to this guy, so therefore it's just this will be equal to x is equal to x minus the learning rate times the gradient minus gradient. And for my mu here, uh, yeah, that's some typical value, maybe like 0 0.5, 0 0.9, 0 0.99, and so on, this momentum. So as we just kind of like illustrated earlier, like so it allows like velocity build up in some kind of like direction that like shallow direction that means the direction that we have like horizontally earlier. So we have this a little bit component here. We can accumulate to get faster along that direction, and also like uh oops cancel out like dampen the direction that like uh, that have rapid change in the gradient side. Okay, this is momentum, like simple idea. So you see like this illustration, if I use momentum and not using momentum, like same step size here, in the sense of like same learning rate, and it it it's not too bad like in this case, but apparently like with momentum, like I get near the the optimum. Like you can say like here is a sufficiently near the optimum. We get that like in 3 steps here, but here like after 10 steps, the for SGD, direct SGD is still quite far from the real optimum there. So that's the with momentum. Now so there's some modification of momentum. Long as one modification known as this lateral of like accelerated gradient. So the idea is like if we use momentum like uh kind of like by default, sometimes like we may overshoot. For example, like if I have case like this, I compute like this guy, right? This you can think of this as a ball trying to roll into the minimum, right? And at this point here, at this point here, it's actually pretty close to the minimum already, right? But because of the momentum that built up, it will continue to move forward, right? So therefore, like it will kind of overshoot. Uh, so instead, like what the Lester like his idea is like uh maybe I can look ahead. So something like at this point, like for here, I will look ahead to this location already. Like I'm not computing like the gradient at this point, but I try to compute the gradient at this point, like something like. So I look ahead a little bit, so to so that like it's less likely for me to overshoot. So more precisely will be like this. So the difference is like if you look at like in the previous case, we still have this velocity update, right? So we have this update here. This is a my delta x earlier, basically. Actually, I should use a consistent notation. Sorry about that. And I have this is a learning rate earlier. And learning rate actually is a learning rate multiplied by 1 minus mu here earlier. And and that is my epsilon basically. And the difference here is that I earlier I have just xt minus 1. That's basically the gradient in the previous step. Now with the Nesterov accelerated gradient, I will compute the gradient not at xt minus 1, but at the gradient at a in the next step. Basically, like you think about look ahead. I think like if I ignore this term here, I expect that we move ahead like by mu v minus 1, right? So therefore, I will compute the gradient like mu v minus 1, mu v t minus 1 further away from my uh, current location. So is that clear?
Dr.
So
Chang,
yes,
T minus 1, is that just the previous step?
yes, it's just previous
Okay.
step. Yeah. So yeah. So it's like current step update is t. So t minus 1 is previous step. So yes, but the only issue here is that if I implement this like naively, like this is a little bit difficult or like complicated because uh I think of back pop. Like when you do back pop, you compute the gradient and the value at the same time, a gradient and the output at the same time, right? So you don't look ahead, right? You in general, like if you want to look ahead, then you need to actually compute the gradient at different location, right? That's the value different from the current input, right? So but this can be fixed. We can modify that. Like think of like this is the original NAG. If I just reparameterize that with like uh, this as a xt here, so or like this as x, this one as x tilde t minus 1 here. So then I can reparameterize everything. Then x tilde t is equal to this guy, and xt, I know that xt is what? Xt is equal to this one, right? Xt is equal to this one minus mu vt minus mu vt here, and I know x tilde t minus 1, so xt is equal to t, wait a sec, xt tilde t is equal to this one, so x tilde t minus 1 equal to xt minus 1 plus mu vt minus 1, right? Then therefore I can move this to the other side, so I have xt minus 1 is like x tilde t minus 1 minus mu vt minus 1. And then I can group the terms here. So I have like mu here, group together vt minus 1. And let's see. Uh, so yes, then we have the update, say x2 t2 um wait, okay, I want to make sure I didn't wait. Okay, then I update with this xt instead, xt tutor instead. uh so can I find vt easily? Let's see, vt and vt minus 1. uh vt is my current. Okay, vt is equal to this guy. Okay, vt is equal to this guy. Oh, okay, it's okay. VT is based on update of, yeah, that's exactly right. So I have like I can I basically in this case I will keep VT I keep basically storing. So after the entire thing I will have equation, this one and this last equation, right? X tilde t, these two equation. Now the difference from before is like I will be updating VT and X tilde t instead, and my VT can be updated by this guy, right? I know what's VT minus 1 x tilde t minus 1, so I can be updated with this. And then my x tilde t is updated by this guy here. So, okay, everything is great. So I'm not cheating anywhere. So, and this is another illustration with energy. So it looks like it does not overshoot as much. So you see like here, like if I use momentum, oh, of course, in this case, it doesn't look like it has much more gain, but you can see like the effect is it doesn't overshoot as much. So if like if momentum I overshoot a bit more, but I energy I don't overshoot as much. So I follow more closely. Uh, so and and another idea like is known as AdaGrad. The name, as the name suggests, is a adaptive gradient. So the idea is like if you think of like for example, like in this case here, uh, uh, or what I want to say. I guess this is not a good example. I mean, like this, it's hard to illustrate like from this example. But idea, like you can imagine, is like you may have like uh, trying to you have like several dimension you want to optimize, right? Several dimension, and in one dimension you already have like several updates. For example, you move a lot in one dimension, right? Like a lot here, but you didn't move a bit in the other dimension, so you don't have like many uh, accumulated movement in the other direction. So maybe like since you move so much along this direction, maybe uh, you are already for this direction you are already quite a bit close to the optimum. So therefore, like maybe I don't want to have this direction move that much. Or you think of this other way will be like because uh the other direction like it haven't moved a lot yet, then maybe I should give them more opportunity to explore this other direction. So relative to this direction is here. So therefore, like I if I think of uh, if I think of like these two uh what should I say, like these two delta, or like the change the update like for these two like separately. So maybe I want to like scale down this a bit more for the case that for the direction that I already explore a lot, and allow the other one maybe scale up a little bit. So then in that sense it will be like I can scale down the direction by the accumulated uh, gradient in that direction, or the accumulated uh, I shouldn't say gradient because gradient is a better accumulated derivative along that direction. So, and in practice, I will take the accumulated square derivative. So I will take the square of that, like basically along this one, each time I move this way, I'll just say like, for example, first step, like I will have like this much change here. And then the second step, this much change here. I'll square all of them and I add them all together. And I use that to scale down that direction, basically. So my dx, so therefore, let's see. So therefore, my dx is scaled by this thing here, by this cache here. The cache is essentially just a sum square of the previous derivative along that direction. So and this is like known as adaptive gradient, and okay, this is an illustration. So you cannot see much from here, I guess. So I like to mention this adaptive gradient because by itself may not be, I should say, the best performing uh, technique here, but it was used in several like kind of like modified technique. For example, like this RMSProp is essentially it's exactly doing this AdaGrad here. So it's I have this AdaGrad step exactly. Okay, it's actually this is RMSProp, but the only difference is like he is using the moving average of the cache. So like in many cases here, like earlier, like we use the moving average of the update and here like use the moving average of this normalization factor instead. So that's the RMSProp. And an interesting remark here is like this paper, this work is never published. It's like actually Hinton like just present that like in his Coursera course in 2012. And then like, when people like cited this paper, it's just like cited whatever like lecture 6 of the Coursera course or something like that. And this is our MS pop and this also is yeah, it's actually for this case it's actually pretty nice. Yeah, I don't know. So and finally like talk about Atom. I guess most of you heard of Atom. Atom is like uh basically like considered the state of the art. Like even though it was introduced like for several years now, so still like uh for many people like trying to train neural network, the first thing they try probably just use Atom. Um, so Atom actually just merged like several ideas that we mentioned like earlier. So it it is have this RMS pop like you have compute what's that the second moment to normalize the your derivative, like basically like this is the cache earlier, the v is like the cache earlier, we have this one here. And also like we have the momentum update, so we have also like the changes is like kind of like smooth that or dampen that like with a moving average as well. So we have m here like this. So this is basic Atom. A superly well cited paper, very influential paper, but the idea is actually pretty simple. But of course, it has this analysis in the paper, also like uh, yeah, nice analysis there that I guess very few actually bother to look into unless you work in the optimization area. So and yeah, that's basically. But a little bit maybe a caveat, but it's not really major. It's like uh, because we have this uh, in it, when okay, we have this compute this first and second moment that we had earlier, but in the initial step when for the first couple update there will be like some bias here because when I have do the moving average, consider like for example the second moment here, when I start with like I don't have the value for the second moment, right? I just plug in zero here, right, for the beginning. So therefore it will be a lot of bias. So what they did is they simply divide that by 1 minus beta 2 to the power t. So you see like when t is equal to 1, let's say the first step here, then this 2 will go cancel, right? Then we'll be just get the original moment, second moment. Uh, on the other hand, when t is getting big here, so beta is supposed to be less than 1. So then this will eventually just equal to 1. So then the scaling factor eventually will diminish and disappear. So okay, but that's basically the entire atom. That's it. Pretty simple. Um, and so I guess of course like one thing you see like that's like for all these approaches here, like the learning rate is some hyperparameter. So we need to basically predetermine like what is the learning rate. So you can oftentimes people just randomly pick a number like 0.01 or something like that. And you may decrease the learning rate over time because when you get closer to the optimum, typically, uh, like for example, like in this one here, of course this is not a good illustration, but you're getting closer and closer to the optimum value here. You tend to need to make the learning rate smaller. Otherwise, you're likely to overshoot or never really get to the uh, real optimum. real optimum value. So therefore, like one way you can do is say just set a so-called scheduler to schedule your learning rate to get smaller over time. And like this one, like when you are, or like you can set a plateau also, like if you whenever like you consider it's a near plateau, you just like lower the learning rate and something like that. In PyTorch, for example, there's a option for scheduler, like, and there's also like, but the scheduler for like this plateau is I never use that actually because um let's see, let me go back. So yeah, unfortunately I didn't put the slides here. I put it somewhere here for the near dropout. I guess I talked about the regularizer. So one remark I also want to mention is like yeah, about this one. Um, Another way to do scheduling and quite fashionable is like doing this cycling scheduler. So basically like this. So you have compared this standard learning rate scheduler is that you, as I showed earlier, you kind of like let it go like for a while. When it plateau, you just reduce the learning rate by half of something, like by 1/10, and then you go down again or something like this. So another approach is like you just have a kind of a cyclic change of learning rate. So you have like this very rapid cycle here. You go down quite a bit, and you have a large learning rate, and then you go down quite a bit, and then like you shoot up again. I have a high learning rate, and then go down again. So the advantage here is that you can think of like whenever you go ups and down, it's just actually like each time is like you are training a different model. Uh, you now what you get is like an ensemble of a training model instead of like one model. And as we mentioned, like previously, this is a little bit like the idea of dropout as well. You have like an ensemble of models, um, and you combine all of them together, you tend to get like a better result than like uh, the 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 individual model. So in this case, maybe you can either like take the best model here, you go ups and down several times and take the best model here, or you can take the weighted average of the all of this model, trained model, and potentially can give you a better model than the original one, or like independent, any of independent one. So this is like one possible scheduling, or like there's another scheduling, it's just one cycle. I don't have a slide there, but it's like just one cycle. Like you can just go to, if for example, if you use PyTorch, you can just okay, maybe I can just show you. Do I have a, let's see, do I have wait a sec. Maybe I just take this one here. It's the scheduler, let's see. Okay, I need to look for that. Unfortunately, let's see. Oh, I'm not sure I use scheduler in this code here. Let's see. Schedule step, and right there, define scheduler. Oh, actually, probably faster, but let me just Google that. Let's see. Oh yeah, it's under the optimization package. Sorry. Is that? Let's see. Optimum scheduler. Oh, okay. LR scheduler. Okay. So you can see that there's a bunch of the one I mentioned is the cyclic scheduler. You have this reduce the learning rate on plateau, like this one here. And then also there's one that, let's see. That's one.
I've used Lambda LR before, and that one's pretty cool because it lets you kind of define your own function.
Oh, this lambda error?
Yeah, you can define a lambda.
So did you try something like interesting like that learning rates that make?
It wasn't very interesting. It was kind of just a modified cyclic learning rate that I did.
Okay, yeah. So this one cyclic was supposed to be good. At least I watched a this was like a fast AI a lecture by some fast AI people. He said like this one he think is the best. Right? But when I tried that, like it wasn't that. But I think like one thing is like pretty nice about this package is like it's not just like you. What I want to say uh the API is great, and at the same time, like you can easily use it as tools to find references because you see like what people are actually use, right? For example, this one cyclic LR here. Let's see, I shouldn't DIR, but instead like oops, can I go bigger here? So yeah, the nice thing is like if you want to figure out where is the paper coming from, they usually have the link as well. Yeah, so then you realize like actually this would be nice if you want to dig deeper into research. Um, so for example, if you want to see like yeah, someone say like it's something this one is good, then yeah, maybe you can come back. Like for me, like I don't do research on this here. I mean, on in this particular area, so I didn't really read this paper. But maybe you are interested in, for example, like getting better optimization or really interested just like in this area, then maybe you can just go take look for this paper. And from the API, it's easy for find the link. For example, like maybe it's not so obvious like where you have the paper, right? But here you can find this paper just reading the documentation of the API. So okay, this is like one remark I want to say. So let's see what next. So okay, next thing I like to probably quickly go for, but not as detailed as I did like in the past, is like to talk about like second order optimization. Um, so for the second order, like it would be more. Let me just like use here maybe. I always have this problem. Like after a while, I don't know where I put the pen. That's where's that? Okay, here. So start a new page here. So for the second order optimization is I let's think of like, maybe I just copy this. You have a function. Why I cannot copy this? Okay, let me just write it. Okay, so I have some function. Let's say that's some L. That's the loss with some parameter theta here. That's the weight here. And I can, in first order, like I would just kind of like approximate this as a L. Let's say like my current, or maybe I write like this. Maybe yeah, it's okay. Maybe I like, yeah. So maybe like I start with some theta naught here, the current location. I want to get it smaller, right? So first order, like I just look at the gradient, right? So I have like L theta will be approximately equal to uh, L theta naught, the gradient L theta naught times theta minus theta naught, right? Something like that. So that's the first order, like Taylor series expansion, right? And I will try to, so if I go yeah, if I go to a steepest descent, then I will just have yeah, I actually okay, let's forget it. This is one kind of like first order case, right? And then the second order, now if I do a second order, then I should add a second order term, right? Second order term, let's say theta minus theta naught, Hessian matrix, theta minus theta naught. So this Hessian is basically something like partial L, partial theta, theta 1, partial L, partial theta 1, partial L, partial theta 1, partial L, partial theta 2, and there's a partial L, partial theta 2, partial L, partial theta 1, and so on and so forth. And wait. I'm sorry. I made a mistake here. The second order derivative, right, should be partial L theta 1 partial theta 1, right? And then partial L square theta 1 theta 2, something like that. So again, a super simple question that make sure you guys are here. So let's say this dimension of this theta is n. So what's the size of this h here? So let's say like theta is an n-dimensional vector. Yes. I'm here, I'm a little bit sloppy. Maybe I write better here. Let's say everything is a vector, then maybe I should put the transpose here. Like everything is a column vector. Let me put a transpose. So it's a partial L theta naught here, let's say. So this should be like have a transpose here also, right? So this is a scalar, right? So this is a scalar. This is supposed to be scalar. Right? It's a row vector multiplied by a column vector. This is a row vector multiplied by n matrix multiplied by column vector. Again, it's a scalar. Now for this guy, like if I want to minimize that, like I take let's say this thing to be minimized when what this okay, this is actually just a quadratic function, right? I can if I this L theta to be minimum, I should have like the partial derivative equal to zero, right? So this should be equal to zero. Actually, this partial derivative is actually just equal to partial L partial theta minus theta log here, right? Because I theta, I mean, this is a constant, right? This two is the same. And this is actually equal to what? This is a does not depend on theta or theta minus theta naught, so it's a zero. And the second one is a just gradient L theta naught. And then this one will be just plus h theta minus theta naught, something like that, right? So this is equal to zero. So therefore, like the optimum theta here is equal to theta naught. Okay, maybe I do one more step here. So h inverse gradient of L theta naught is equal to theta minus theta naught, right? So therefore, theta is equal to theta naught plus, wait, my sign maybe is incorrect. Why I have a plus here? I think I'm expecting a minus. Let's see. Why I have a sign? Yeah, I don't have enough coffee today apparently. So anyone spot the spot? So anyway, okay. Let's don't worry about the sign. Like I said, this either I'm right here or the nose is incorrect here. So um but yeah, my nose is negative, but from here I don't see why it's negative. It seems to be positive. So, but anyway, so the point here is that you see like this update is very similar to what we have in steepest descent, right? So we have basically a gradient, we have the current position, right? Updated by this guy. But the point is that there's no learning rate here, right? So I have a matrix multiplied by this gradient directly. I don't need I don't need the learning rate. There's no learning rate. This is actually one benefit here. Uh, so the update is kind of, I don't need a hyperparameter. However, the problem is like, you think of like, as we say, the dimension of n, like let's say this is typically like theta is a pretty high dimension, right? And h n by n, do you know anyone know what's the capacity doing an inverse of like matrix n by n? Approximately, do you have the idea? Compute. Uh, yeah, actually, n square would be pretty nice. It would be actually more than. Think of like when you do the inverse, at least you need to go for each of the element. Go for each of the element is already n square. The capacity is actually n cube, and I'm think of like because this is the size of the parameter, right? So typically it can be really, really kind of big. For example, like if you think of like just Westlet or something, it's easily over 1 million, right? So then like this will be kind of like not computable essentially. So that's why like typically like we have this is like the basic the what people want to do, but in in practice it's okay. I mean this fine. Yeah. So uh in 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 practice like this one uh uh this one you cannot compute. Basically you can compute H inverse directly. So therefore, like all these approaches, say for example, like BFGS or like that's very probably you heard of that or like LBFGS. All these approaches is actually. By the way, this is like this update is essentially just known as the Newton method, right? So it's just like approximate the Newton method by approximating this like inverse Hessian. So instead of computing the exact inverse Hessian, so we're just going to approximate this inverse Hessian and then update for the theta here. So and how we are going to approximate that? So let's see. Okay, know that like by I'm not sure I should go into detail even. Uh, so maybe I probably won't go into detail, but let's say like the idea here is that if I update this h here, what I'm going to do is I'm going to approximate this h um into a first order or first yeah it's first order first degree or second degree should be order degree, let's say first order second order matrix, right? Uh, or I should say it shouldn't be order or degree, like matrices of rank 1 or rank 2 updates. For example, like I can have H as a like okay, let me call H inverse as B here. So let me call this as B here. B equal H inverse. So let's say I have an approximation of B here. Let's say B K here. So what we are going to do is I'm going to update from my previous BK into my new BK with a rank 1 or rank 2 update. So basically it's like B plus a rank 1 matrix would be like something like U transpose, let's say UV transpose. So where U are a column vector, this is a column vector. So this will be a rank 1 matrix, right? So this will be a rank 1 update. And you will get an algorithm for that, but typically this is not the algorithm people will use. The algorithm people will use is doing rank 2 update. Rank 2 update is I have like BK plus 1 is equal to BK plus UV, maybe plus like W, let's say UVW. uh, oh, okay, what is it? Maybe alpha beta, I don't know. What is good better? UVW X, Y, C, maybe WY, let's say, WY, let's say. So these two rank 1 matrices add together in general will be a rank 2 matrix, right? So therefore, like this will be a rank 2 update. So then the key here is like how to figure out like what are these things here. And this is actually BFGS belong to one of these thing here, one of this rank 2 update algorithm here. And let's see. And okay, maybe here, as I said, I'm not going to into detail of deriving this stuff, but let me just give you an idea like what you're seeing in practice. So say for the rank one update, the rank one update. So I'm not going to derive that, but the rank one update will be like this. I will have like bk plus one, or maybe I use this like bk plus one and bk plus W transpose over W transpose QK, where QK is equal to gradient of L for K step minus gradient of, or maybe don't write like that, gradient L, let's say theta K plus 1 minus gradient of L theta K, something like that. Maybe I use K and K minus 1, I say. And then I have PK. I don't have PK here. So, okay, let me define PK here. So PK is a theta K minus theta K minus 1. And then my W here, so I have QK here, my W here will be something like PK minus BK QK. So by the way, if we want to really get into kind of like if you are actually interested in that, like I'm just thinking like because I for the last several years I go into detail deriving this, but I don't feel like students actually are very much interested in the derivation. So this time I guess I will just give high level and just like give you some equations, and then like if you're interested, like you can just go back to my last year's Course website and go to that link to the presentation like that. I actually go to the detailed derivation of this one. So and for the rank 2 update here, so rank 2 update. So for the BFGS, so BFGS I what so for BFGS, what is actually going on is we have as I mentioned, there is a rank 2 update, right? Actually, it have HK plus 1 will be updated as HK plus 1 minus alpha U transpose, but 1 over beta W transpose. Oops, I didn't copy that was U transpose W transpose here. Let's see if I W is like the same as before. W is a PK minus BK QK, and my U here, let's see, my U here is equal to 1 over V transpose PK QK minus HK PK. So again, I derive all of this in the past. So if you are interested, you can go back to my previous video, like I mean video from my previous year. So actually from here, we of course the BFGS that we have this update like computer for HK the hashing, but we are interested is actually update of BK plus 1, right, for the inverse hashing, right? So from here to here, actually this is like the part I'm not able to derive that, and I cannot find anywhere like explain like so. But this is like I try to verify that like using Okay, numerically that's correct, but I don't know how to prove that or derive that. Uh, I gave extra credit to students in the past to try to derive that, but over like 2 3 years, no one bother or like managed to finish that. So therefore, like I don't know. So, but if you try to do some very complicated algebra that I was stuck, that like you can show that this is actually equal to PK QK transpose over QK transpose PK BK I minus QK PK transpose uh, QK transpose PK plus PK PK transpose QK transpose PK. Yeah, something like this. So that's basically the update, right? So you know that like all this QK and PK is just it's just a vector, right? So it's just a column vector. And I form this is like okay, this is actually formed together with a matrix, right? But it's not too bad. Like I have like this matrix multiplied by this and multiplied by this matrix, not too bad. Uh and uh and this is how I update like BK to find the leaks. Uh, and then we can iterate many times to find the uh, find the inverse. Or you can just do it one update. Actually, do it one update is okay. And then use this to approximate uh, your optimum value. So once you get this PK, BK again, like you can use that to go back to up here, right? So then you can find that optimum theta star is just like your current theta plus like this would be like your H inverse is actually might be here uh, multiplied by the gradient. Okay. So this is actually the BFGS. Yeah, this is the BFGS. So how about LBFGS? So the LBFGS is something like if you think of this entire thing, not to say like computing BK, the problem is that storing BK can be quite expensive even. So because you can have like this matrix, maybe even like, of course, I'm quite sure if you use like GPT, they are not going to use BFGS. But let's say like you have like a million or like 10 million parameters, then you have a matrix is like 10 million by 10 million. It's pretty huge. So you don't even want to store this matrix. So what we can do is like instead of like storing PK here, we'll just say storing QK and PK, but not storing just like the current K, but we store like for the PK and QK for the several previous steps. So then what we're going to do is like we are going to iterate this several times. So what I mean is that like we have like BK plus 1 is equal to this one, right? So then therefore like BK is equal to this multiplied by BK minus 1 multiplied by this plus this guy, right? So of course I need to change all these indices here. But um but let's say I can iterate like 10 times, right? And iterate 10 times. Uh and I'm not going to, of course I at the beginning, so what I mean is like uh if I have like for 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 example, like at the moment I need to compute like B10 like for the 10 iterative step here, B10. B10 will involve B9, right? I mean have B8 and so on and so on up to like B something. But let's say I don't have like B like for step 0. I don't know that. I will just replace this by an identity matrix. But that's fine. After so many iterations, the effect of this difference of like B and I may not be that bad. So I'll just use I anyway. Then using this identity, I don't need to store it, right? And yeah, and I know that like for this PKQK, each of them like the storage needed will be just dimension n, right? So let's say if I need to store 10 of them, then I will just both P and Q will store like 20 of them, and and I will need just 20 times a million. Let's say the length of the vector is a million, then will be 20 times millions instead of like a million by million. So, okay. And that's basically LBFGS. So I guess this is a very quick uh, uh, explanation of the second order BFGS and LBFGS. So uh, yeah, it's time already. Anyway, so I will stop here and then I will come back on Thursday then, unless you guys have any other questions. Yeah.
Just a quick question.
Yes.
So the motivation for the second order optimization, is it just that we don't have to deal with the learning rate, or is it are we trying
It's
to
actually potentially is better. It's just similar to you do a Newton methods to do find the optimum values. If you know, for example, if I try to find minimum, this may not be a very good example here. You do gradient descent. What you're going to do is, for example, start from here. You take this gradient, take this slope here, right, and then multiply by the step size, whatever. Maybe like this is steeper, then you go down that much, right, and then go move that much here, and then here you have the same slope. You move that much, and then you move that much again. Now the slope go down a little bit, maybe you move only that much, and so um I'm comparing to first order method. The second order method, what it did is in 1D, uh, intuitively, it's basically you are fitting a pub, a parabola or like a second order function in this at this point here. So you fit the second order function, and then this is the second order function. Then you immediately know where's the optimum. The optimum will be here. So you jump to here, and then again you fit another parabola or something like that. So theoretically, like it would be faster. It will converge much faster. But of course, like that's theoretically, because computation wise, it's much more expensive.
sure?
And to trade off the capacity here, like you do all this approximation, like do approximate Hessian and then approximate of the Hessian. So it's hard to analyze like eventually how much you lost because of this approximation.
Is
So yeah,
could but there's nothing that says a second order optimization would arrive at a better solution necessarily, right? Or
it
is
will it I guess it's hard to prove this kind of result, but generally speaking, like you will always converge faster if you can do that, ideally. But in practice, so therefore, like the only place like people use this is that like they don't have lots of training data. For example, um, if you know some problem like maybe we'll talk about in the future, is like for example like you see that in the passive for example style transfer, you have like two images, like one have like this image was this the same thing here. So let's say I have one image give this give me the style, this give me the content here, and then merge them together. I need to go for some optimization, right? But in this case, I don't really have a large training batch to do that. I just basically taking like this image and this image as the input. And this case, I doing second order optimization may make sense. You don't actually have so many training data here. It's not like you have like image that you have like a million times so much more training data. And I didn't do the experiment myself, so therefore I don't know how much faster, but I'm aware that like for this kind of problem, like people do use a second order kind of like optimization.
okay?
Yeah.
Interesting. And I have another question, but
Yes.
it's more of an administrative question.
Yes.
I was looking at the schedule, and I
Yes.
noticed that exam 1 is currently set for April 15th. And I
Oh,
was
okay.
wondering, is that a hard date, or is that just tentative?
No, it's tentative. Like yeah.
Yeah, I
It
know it's kind of
depends.
far
Yes.
out. I just
Yeah. It's file.
I'm
Yeah.
I'm planning on it, like traveling around that date, and is it going to be like an in-class test where we just have the class time, or
I will be in class, but you can be doing remotely. So what I mean
Okay.
is I will do the things I put in on Canvas again. I give maybe a 2 hours, 3 hours, or like maybe even less, just to do that. And then
Okay.
you scan and yeah, send it back for Canvas.
Great.
But that's not a hard day. There is a tentative. We can change that. Yeah.
Okay.
So as
Thank
long
you.
as you guys figure out like which days is like yeah, okay, then that's fine.
Great. Thanks.
Okay. So I guess yeah, if no more questions, I will see you guys on Thursday then.
Okay. Bye.
Right.